Okay, May, June 2022, paper 4, variant 3. Question 1. A battery provides energy to an electric car. The electric car has an acceleration of 2.9 meters per second squared when it moves from rest. The combined mass of the car and its driver is 1,600 kilograms. Calculate the time taken to reach a speed of 28 meters per second. We need to find the time if you have the acceleration and the final velocity. The initial velocity was 0 from rest, so u equals 0. We know the equation A equals V minus U over T. If U is 0 and we need to find T, so T would be equal to V over A. So 28 over the acceleration, which is 2.9. This will give you a final time of around less than 10, 9.7 seconds. 9.7 seconds. Okay, now calculate the force required. How can I find the force required? F equals ma. Quite straightforward. Ma, you have the mass, 1,600 times the acceleration, 2.9. What's 1,600 times 2.9? 4,640. Again, you can write it down as just 4,600 newtons. Calculate the kinetic energy of the car when the speed is 28 meters per second. Kinetic energy equals half mv squared. So it's half times the mass, 1,600 times velocity squared, which is 28 squared. So this would definitely be a huge number. Times 28 squared, 627,000. 627,000. You can write it down as 6.3 times 10 to the power of 5 joules. Again, please do not forget the units. Time taken for the car battery to be recharged from 0 to a full charge is 8.3 hours. The charge is delivered with a current of 32 amperes. Find the charge, so I equals Q over T, so Q equals IT. What is the I? Current 32, and the time, it's 8.3 hours. You need to convert it into seconds, so times 60 times 60, or times 3,600 times 8.3 times 60 times 60. This will give you 956,000. Again, you can write it down as 9.6 times 10 to the power of 5 coulombs. Okay. Under ideal conditions, the car can travel a maximum distance of 390 kilometers when the battery is fully charged. Suggest why it is in normal use the car needs to be recharged after less than 390 kilometers. In real life, it doesn't travel actually 390 kilometers. It actually travels less than 390 kilometers. Why is this the case? Well, sometimes you have some losses. Ideal conditions actually would be if the car is traveling with the least amount of air resistance, for example. So if you have any wind facing the car, this would increase the amount of air resistance, therefore increasing the force, and so the distance wouldn't be as much. The distance would be much less than 390 kilometers. That is one practical problem. Okay, so air resistance due to, we can say, air resistance due to wind facing the car. If you have some wind, you'd have a lot of energy wasted. Water is held behind a dam. State the main form of energy stored in the water behind the dam. Definitely the energy stored would be gravitational potential energy. Please write it down as gravitational potential energy, not GPE. The water is released from the dam and falls vertically at a height of 410 meters at a rate of 480 kilograms per second. 480 kilograms per second. Calculate the rate at which the energy is transferred. So rate of something means that we need to divide this something by time. Do you have the time? Do we have the time? Actually, we do have the time, which is per second. He said 480 kilometers, kilograms per second. So this means that every second, this is the time. This is the time taken. How can I find the gravitational potential energy, or how can I find the rate, which is the power? So power equals energy over time, or gravitational potential energy, in this case, mgh over time. The mass is 480 kilograms per second. This is the rate of the mass, g 9.8, height 410, and the time is only 1 second. Time is only 1 second. So 480 times 9.8 times 410. This is 1,928,000. So 1.9 times 10 to the power of 6 times 10 to the power of 6 watts, because this is power. You can say watts, or you can say joules per second. Definitely watts would be better. The power scheme supplies a current of 270 amperes at a voltage of 6,000 volts. Can I find the efficiency? Yes. If I have the power, the original power, can I find the second power? So power equals IV, or BI. 270 times 6,000. What's 270 times 6,000? This is 1,600,000. 1.6 times 10 to the power of 6 watts. To find the efficiency, useful output, efficiency equals useful output over total input. What is the useful output? Which of these would be the useful output? Again, the useful output has to be the smaller number. The smaller value would be 1.6 times 10 to the power of 6 over 1.9 times 10 to the power of 6. If you want to find it in percentage, you can multiply by 100. What's 1.6 divided by 1.9? This is 84%, around 84%. Okay. Okay. Now, hydroelectric energy is a renewable form of energy. State one disadvantage of hydroelectric power schemes. One disadvantage of hydroelectric. What would a disadvantage be? For example, flooding. It causes floodings behind the dam. It can kill some. Can destroy some of the animal habitat. For example, flooding behind the dam. Can say destroy animal habitat. Okay, one other renewable source of whatever, we have several renewable sources, such as, let's say, geothermal. You can say solar, you can say whatever. We have a lot of them. Question 3. Oh, this is cancelled. Not required to solve this question. This is cancelled. Determine the mass of the boat. So if you have the weight, you can't find the mass of the boat. Okay, you'd say that the mass would be equal to the weight over g. Whatever the weight was, you'll just divide it by 9.8. Force is a vector. To draw a circle around two other quantities in the list, which are vectors. Acceleration is a vector. Momentum is also a vector. Question 4. Okay. This question we are not required to solve. Question 3. It's all cancelled. 3A is cancelled. 3II also, if you have the weight, you can solve it. Okay, whenever you can find the weight, which is the force, the resultant force in this question, and then you can find the mass because of this weight. Okay. Question 4. You have an apparatus used to observe the motion of smoke particles, the Brownian motion. Draw the path of one of the bright specks of light. You need to draw the Brownian motion, which is a random zigzag motion, isn't it? A random zigzag motion. So basically, an arrow moving in different directions, okay, randomly with no specific direction or pattern. Also, you have to have sharp edges. You cannot draw curves. Explain in terms of forces and the motion of air molecules the cause of the motion of these smoke particles. So basically, we need to describe what's happening in the Brownian motion. What's happening in the Brownian motion? Basically, that the air molecules move fast and random, colliding with the smoke particles from all directions, causing this random zigzag motion. Small air molecules collide or sorry, okay, move fast and random, colliding with the larger smoke particles from all directions. When they collide with these larger smoke particles, they cause them to move in a random and zigzag motion. Okay, causing a force. Okay, causing a force on them, and they move in a random zigzag motion. Zigzag motion. Okay. The temperature of the air in a sealed glass container is increased. When you increase the temperature of the air, explain in terms of molecules why the internal energy of the air increases. In terms of molecules, why does the temperature of the air increase? Because the kinetic energy of the molecules increases. Yes. The kinetic energy of molecules increases. Explain in terms of molecules why the pressure of the air also increases as you increase the temperature of the air. The kinetic energy increases, as we said, so they move faster and they hit the walls harder and more frequently. So the molecules, okay, hit the walls harder and more frequently. Okay. Define specific heat capacity. What is the specific heat capacity? It's the amount of energy required. Okay. Amount of energy required to increase the temperature, to increase the of 1 kilogram of object, 1 kilogram of an object or of a material or whatever, by 1 degree Celsius or Kelvin. 1 degree Celsius or Kelvin. So it's the amount of energy required to increase this temperature by this mass, this 1 kilogram of mass, by 1 degree Celsius. A bowl contains 500 centimeters cubed of water, temperature 5 degrees. It's then frozen. When it's removed from the freezer, the density of the water is 1000 kilograms per meter cubed. Can I find the mass? Yes, I can find the mass. Density equals mass over volume. Density equals mass over volume. So mass equals density times volume. Can I just multiply 500 by 100 or 1000? Would that be correct? No. would not be correct. Why? Because the volume is in centimeters cubed, and the mass, or the density, is 1,000 kilograms per meter cubed. So I need to change the centimeters cubed into meters cubed. How can I do that? Hmm, Divided by 100 cubed. Divided by 100 cubed. So what's 500 divided by 100 cubed? It would be a very small number. Yes, a very small number. So it's 5 times 10 to the negative 4. That is the volume. So 1000 times 5 times 10 to the negative 4, which would be 0.5 kilograms. 0.5 kilograms. Okay? Hmm. Um, II is cancelled. Latent heat. Latent heat of fusion has been removed. Question 6, figure 6.1 shows crests of plain water. Okay, draw the three crests of water to the right of the barrier. To the right of the barrier. Would this be a narrow gap or a wide gap? Definitely this is a narrow gap. You can measure the wavelength and measure the gap. You'd find them almost equal. When the wavelength is almost equal to the gap, this would be considered a narrow gap. So how can I draw the wave fronts after they pass through a narrow gap? Using a compass. Yes, using a compass. The pointy edge of the compass should be fixated in this point, and then you open up the compass to the first crest and draw a semicircle on the other side. And then as the point edge is still fixated at this point, open it up to the second crest and then draw another semicircle, and then repeat the process with the third wavefront and draw another semicircle. Draw another semicircle. Okay, that's it. Definitely, you need to draw it quite carefully. You wouldn't want to lose marks on being careless. Okay? Figure 6.2 shows crests of a plain water wave in deep water approaching a region of shallow water. So as you're moving from deep into shallow, the water wave moves slowly into the shallow water. Draw three crests of the water wave and show the direction of the wave in the shallow water. Okay, this is easy. What should happen? First of all, you should continue the direction of this wave. Just draw a straight line using a ruler. Draw a straight line until this wave reaches the barrier. So this is the direction. This blue line is the direction. And then at this point, you need to draw a normal line. Drawing a normal line at this point. Definitely you need to draw it with a ruler and make sure it's 90 degrees and all this. Okay. Make sure it's 90 degrees at this point. Okay, not bad. And then as you're moving from the deep water into the shallow water, what happens to the wave? It refracts. Does it move away from the normal or closer to the normal? Does it bend towards or away from the normal? It would bend towards the normal. Why? Because the speed decreases. As you move from deep into shallow, the speed decreases. So the direction would move somewhat in this direction. So it moves somewhat in this wave. This is the direction of the waves after they pass into the shallow water. How can I draw the crests? How can you draw the crests of the wave? Drawing the crests of the wave, sometimes the marking scheme would want you to at least have one of these waves, at least one of these waves touching the original wave. So if I start from this point, so it's touching this wave, okay? It will bend. Yes, it will bend in which direction? This direction. And then I need to draw two other waves. How can I draw the two other waves? Make sure that they are closer together and that they are perpendicular to the direction of the motion, to the direction of the motion of the wave you have drawn. These three lines, these three wave fronts should be should have equal distances. They should have equal distances, which are the wave lengths. And you should make sure that these wavefronts are perpendicular to the wave that you have drawn. Make sure that they are perpendicular. Okay? Okay. So this is the direction of the waves after they have passed into the shallow water. State two waves, two ways, not waves, two ways in which direction or in which transverse waves differ from longitudinal waves. How do transverse waves differ from longitudinal waves? Well, transverse and longitudinal. Let's say, for example, that the transverse move up and down, perpendicular to the energy motion, right? And you can say, for example, that they, let's say they move up and down. Let's write down the transverse waves. Okay, transverse waves move up and down perpendicular to the energy motion, right? What else? We can say that the longitudinal waves have compressions and rarefactions, or you can say that the transverse waves have crests and troughs. Okay, transverse waves have crests and troughs. Okay. State the typical value of the speed of sound in water. What is the typical value of the speed of sound? 1,500 meters per second. State why sound travels faster in water than in air. Because the molecules are closer in the water. Okay, molecules are closer in water. Okay. Figure 7.1 shows a plane view of a room. A plan view, not a plan view of a room. So you're looking at the room from the top view, actually. Okay, there's a plane mirror. There's a plane mirror and a picture across the whole of wall AB. So wall AB is a huge picture. Person standing at point X and is looking at the mirror. The person cannot see all of the picture on wall AB. He cannot see all of the picture on wall AB. There's a point P on wall AB, which is the closest point to A that the person can see reflected in the mirror. So if the person is standing at X, he's looking towards the mirror, he can see only part of the picture. He cannot see it all. We need to find a point P on the mirror, on the wall. Point P on the wall, which is the closest point to A, A that he can see on the mirror. So if you think about it, okay, don't draw just yet. Let's just think about it. What happens if I draw a line? Okay, this is a line from X to the mirror. What will happen to this line? You need to draw a normal line and then find the angle of incidence and the angle of reflection. So this line would reflect to this point, for example, right? Do not draw yet, just yet. Okay, so he's not even seeing at this point. If he looks at the mirror from this position or at this position, he won't even see the drawing, right? Like, what happens if we increase the angle? For example, if I increase the angle from X, if I increase the angle to this point, to the center of the mirror, for example, and I draw another normal, what would happen? A reflected ray would reach this point, for example, right? So this is the angle of incidence, angle of reflection. So he'd see part of this mirror. Would this be the correct position of P? Would this be the correct position of P? There is a point P which is closest to point A. This is a point on the mirror. It's a point on the mirror. Will it be the closest to A? I don't think so. Why? Can I increase? The question is, can you increase the angle of incidence from the person from point X? Can you increase the angle of incidence? Yes, I can. Does it have to reach the center of the mirror? Can I increase the point? Can it reach this point? Can it reach this point? Or can it reach even this point, which is the furthest point on the mirror? Yes, it can. So let's draw the angle of incidence or the incident ray until it reaches this point, which is the furthest point on the mirror. So how can I draw it? We need to draw a straight line from X all the way to the furthest point on the mirror. Draw a line from X all the way to the furthest point on the mirror. You've now created the largest angle of incidence. At this point, I will draw a normal line and measure the angle of incidence. Since this is a mirror, so you need to uh, draw the reflected ray. Reflected ray would reach, for example, this point. Again, you're drawing using your protractor and ruler and whatever. You need to measure the angle of incidence, make sure it's equal to the angle of reflection, draw the angle of reflection, and reach the point on the mirror. That would probably be around this point, and call this point P. This is how you can reach the maximum distance or the closest point to A. This would be the closest point to A. Why? Because you've increased the angle of incidence as much as possible. Okay? Hmm. State two properties of the image formed by the mirror. Two properties of the image formed by the mirror. We have several properties. For example, that it is always upright. It's always virtual image. It's always the same size. Same size. Virtual. Upright. Visible light is an electromagnetic wave. State the name of one region of the electromagnetic wave, which have shorter wavelengths than visible light. Shorter wavelengths, meaning higher frequency. So, for example, you can say gamma rays. Longer wavelengths, you can say radio waves. Okay? Figure 8.1 shows a circuit. State the name of component X. X is an LDR or a light dependent resistor. Light dependent resistor. The potential difference across component Y is measured with a voltmeter. On figure 8.1, draw the symbol for the voltmeter and its connections to the circuit. Can I draw a voltmeter across component Y, which is a fixed resistor? Okay. A voltmeter across component Y. Okay. You can draw it to the left or to the right. It's okay. You can do either. Now, the electromotive force on the battery of the battery is 12 volts. 12 volts. The component Y has a resistance of 400 ohms. 400 ohms. It In a brightly lit room, the resistance of component X is 350 ohms. 350 ohms. Can I find the current in the circuit? Okay, I can find the current. So I equals V over R. The total voltage would be 12 and total resistance is 750. What is 12 divided by 750? A rather small number, 0.016 amperes. Okay. Calculate the potential difference across Y. Can I find V? V equals IR. That's easy. So 0.016 times the resistance of Y, 400. What's this times 400? 6.4 volts. Okay, not bad. In a dark room, the resistance of component X is very large. Okay, we know that because as the brightness decreases, the resistance increases. State the effect this will have on component Y. So, as the resistance increases, he said as the resistance in the LDR, as the resistance increases, what happens to the voltage? Voltage increases. And he say that the resistance of component X increases, so the voltage or the potential across component Y decreases. Decreases. So, for example, if they had voltages of 6 volts and 6 volts, if you increase the voltage to 9 volts, if, for example, the voltage is 9 volts, so the voltage or the potential difference of Y would be only 3 volts. Why? Because the total voltage has to be 12 volts. So just say practical use for component X and LDR. LDR. For example, we can say the street lights. A lot of street lights use the LDR component. Street lights. Okay. Figure 9.1 shows a magnet on the end of a spring and a coil of wire. Okay, the magnet is pulled down and released, so it keeps on moving up and down. Describe and explain what happens to the needle of the sensitive galvanometer. What happens to the needle of the sensitive galvanometer? Well, yes, it moves. Yes, it keeps on deflecting to the left and to the right. As the magnet moves on up and down, the needle keeps on deflecting to the left and the right, and then we need to explain what's happening. So the galvanometer, okay, the needle deflects to the left and right. Why? Because the magnet moves, as the magnet moves, it cuts the coil, cuts the coil, or instead of saying that the magnet cuts the coil, okay, instead of saying the magnet cuts the coil, you can say that the magnetic field lines cut the coil. The magnetic, okay, the magnetic field lines cut the coil, inducing, okay, inducing an EMF and current in the coil. Need to say as it's moving, it keeps on cutting, okay? It keeps on cutting the coil, inducing a current and EMF in the coil. Okay, the magnet is replaced with a stronger magnet. State the effect of using a stronger magnet on what happens to the needle of the galvanometer. So what happens to the stronger magnet? If you use a stronger magnet, what happens? It will have a larger deflection, yes? A larger deflection. Step-up transformer is used to step up the output voltage of a power station from 25,000 to 400,000. The number of coils on the secondary is 36,000. Find the primary coil. Okay, VP NP equals VS over NS. VP is 25,000. We do not know NP. VS is 400,000 over 36,000. Okay, so cross multiplication. If you cross multiply, it will give you 2,300 coils, 2,300 turns on the primary coil. Student places a sample of isotope ruthenium near a radiation detector. And then you have counts, okay, 0, 20, 40, 60, count rate, okay. Figure 10.1 shows a graph of the count rate due to this sample against time. Explain why the readings in the table are not the same as plotted on the graph. The table, you start off with 101, and in the graph, you start off with 80. Why is there a difference? If you read this statement again, figure 10.1 shows a graph of the count rate due to the sample alone. Due to the sample alone. So this difference is due to what? Is due to the background radiation. It's due to the background radiation. So we plotted the graph without the background radiation. Okay? Due to background radiation. The graph was plotted without it. You removed the background radiation and you plotted the graph. Using the graph, determine the half-life of this isotope. Okay, can I find the half-life? So you have the graph without the background radiation. You start off with 80. 80 divided by 2 is 40. So from 40, we need to draw a horizontal line. And then at this point, you draw another vertical line. Okay, which is at 72. This is at 72 seconds. The nuclide notation of this isotope, it decays to an isotope of uranium by beta emission. Okay, we need to write down the equation. How can I write down the equation? So protonium Pa 23491 gives off uranium plus beta. We know that beta is 0 and -1. So the mass of protonium would remain, the uranium would remain the same, but the atomic number would increase by 1. Why? Because -1 plus 92 is 91. Okay?